Good morning, everyone. Today we will see mathematical analysis using induction method. Uh, we are generating reconciliation for the given algorithm to analyze the correctness and time complexity of the process. The algorithm is designed to solve the problem. We have to check whether the algorithm produce a correct result or not, or how we can achieve the better performance in terms of time complexity using mathematical recurrence equations. And this recurrence relation is a mathematical equation that can be solved using induction method. Mathematical analysis using induction method is a powerful tool for checking the algorithm correctness and for finding the time complexity in terms of order of growth. This algorithm involves the concept of recursion and iterative process. Recursion means the algorithm calls itself is called recursion algorithm, and that can be analyzed using iterative induction method. And next one is looping process or iterative process. It represents looping statement for loop while loop. How the algorithm can be analyzed using mathematical induction method. What's the initial condition for loop? When is the termination statement or condition for the looping statement? And what's the termination statement for recursive algorithm? That can be verified, and the correctness can be verified by using mathematical analysis method called induction method. It involves establishing a base case and an inductive step to show if a property holds for specific input. Now we are assuming that the algorithm works correctly for smaller size of input, and we can uh, prove or assume that the algorithm also work correctly for k size of input, and our aim is to prove the algorithm also works for larger size of input, that is the induction method. First we are checking for smaller size of input, then for k, then k plus also. So like that we have to verify the correctness of algorithm. This method allows verification of algorithm behavior across different types of inputs. And what are the concepts in induction method? First one, base case. The initial condition must be proven. That means the given statement or the recursive algorithm or iterative process is true for smaller size of input. For example, for finding maximum number or minimum number, we need at least two inputs. For finding sum of values, we need at least two values. That is called minimum number of inputs. So the base case represents we are proving that algorithm works for minimum number of inputs. And inductive hypothesis, our assumption is the algorithm works correctly for k size of input. So k is greater than or equal to minimum number of inputs. So our assumption, we have to assume that the algorithm also correctly works for k size of input. And next one is inductive step. What is inductive step? The critical part when you prove that algorithm works for k and also it works correctly for k plus 1 input. So this is called inductive. We have to prove the algorithm works correctly for k size of input. Then the algorithm should work correctly for k plus 1 size of input. That is called induction method. So we know the base case initial condition which is true for the statement, and also the algorithm works correctly for k size of input. That is our assumption. And using this assumption for k size of input, we can prove that algorithm correctly works for k plus 1 input size also. That is called induction method. Then how it works? To prove the statement P of n, the statement can be anything. It's a recursive algorithm or iterative statement for loop, while loop, or any mathematical formula, matrix multiplication, any formula we can prove that can be taken as a statement P of n. N is input size. That is which is true for all integers which is n greater than or equal to n naught. N naught is minimum number of input for particular algorithm, and n is number of inputs which is greater than or equal to n naught, minimum number of inputs. And base case shows that the statement holds true for initial value n equal to n naught. So initially the statement or the algorithm works for n naught, that is minimum number of inputs. So P of n naught is true, that is the base case. So the statement is true for initial kind of statement, that is minimum number of inputs n naught. So B of n naught is true. And inductive hypothesis, our assume that the statement is true for some input which is n is equal to k, for any number of input which is k greater than or equal to n naught. So our assumption is the algorithm works correctly for k number of inputs where k is greater than or equal to n naught. And what is inductive step? We know the base case P of n naught is true, and our assumption is P of k is true. And now the induction method, we are going to prove that P of k plus 1 is true. That is our target. We have to prove algorithm works correctly for P of k plus 1. So that is, we can prove P of k plus 1 using P of k. That means we are proving P of k plus 1 using P of k. If all three steps are satisfied, the statement is true for all number of input. That is, base case is true, and for k inputs, the algorithm works correctly. For more than k also, algorithm works correctly or the statement is true. So finally, we can conclude that um, this algorithm works correctly for all size of input, which is n greater than or equal to n naught. And example, to prove the time complexity of n natural number is 1 plus 2 plus up to n equal to n plus n into n plus 1 by 2. This is a equation, a summation equation of natural numbers. So that short form is n into n plus 1 by 2. Now we can prove n into n plus 1 by 2 is true for the given series. We are going to prove the result. So initially, there are three cases: base case, inductive hypothesis, and induction step. The base case is minimum number of input. If n is 1, the n value is 1, the left side remaining term will be vanished. So left hand LHS value is 1 in this equation. And we are going to find RHS value. RHS is 1 plus 1 into 1 plus 1, that is 2 by 2. The answer is 1. Now LHS is 1, RHS is 1. Both are equal. So the base case is true for the given expression. And inductive hypothesis, we are taking some number of input size, that is k. Now we have to assume that the algorithm works correctly for k size of input. That is, P of k is true. Initially, the base case P of n naught is true, and now this case P of k is true. Now, so if n is equal to k, now the relation can be changed to 1 plus 2 up to k equal to k into k plus 1 by 2. Instead of n, we are giving k value. So 1 plus 2 plus up to k, which is equal to k into k plus 1 by 2. This is our assumption. So we know the base case n equal to 1. That is true. We proved for base case, and hypothesis, our assumption is the algorithm works correctly for k number of inputs. This is our assumption. Next, inductive step. So we know P of k is true. Now we are going to prove P of k plus 1 is also true. So substitute the value. So after k, 1 plus 2 plus k, after k, the next term will be k plus 1, because each term is incremented by 1 to get the next term. So the series will become 1 plus 2 plus 3 up to k. Next term will be k plus 1, which is equal to, substitute the value of k in summation equation. That is n into n plus 1 by 2. Here n is k plus 1. So k plus 1 into k plus 1 plus 1 by 2. That is n plus 1. Instead of n, substitute k plus 1. So now this is the equation. Now we are going to prove the statement is correct or not. Now take LHS, left hand side term, that is k in 1 plus 2 plus up to k plus k plus 1. So we know from the step 2, 1 plus 2 plus up to k is k into k plus 1 by 2. The remaining term will be k plus 1 that we can write. Now, what we can do, denominator 2 is commonly taken as for both the terms. So k into k plus 1 plus 2 times. We are dividing by 2, then that is multiplied 2 times of k plus 1 by 2. Now k plus 1 is common factor for both the terms. So take k plus 1 outside. Then we have k in the k inside and k plus 2 is outside by 2. Now which is equal to RHS. So now we can prove LH, we can take LHS, derive the value and find the RHS value, both are same. So as per the induction method, the given condition or statement are true for all values of input size n. And now, conclusion. The principle of mathematical induction, the formula is n in 1 plus n. Natural of n, sum of n natural numbers, 1 plus 2 plus up to n is equal to n into n plus 1 by 2, which is true for all n greater than or equal to n naught. And what are the uses of mathematical induction? Proving algorithm correctness. So before implementation, algorithm correctness should be verified. After developing algorithm, we have to check whether the algorithm can produce the correct result or not. So this that can be done by induction method. And for recursive algorithm means the function calls itself. When the recursive algorithm will be terminated, if the algorithm control reaches the base case, there's an initial condition for termination. So base case that can be verified by using mathematical induction formula, especially useful for recursive algorithm like binary search, factorial, Fibonacci, and MERSAT. So we can prove the correctness of a recursive algorithm, iterative approach, or any method using induction process and analyzing the time complexity. So that can be used to find the time complexity. That is the order of growth. Uh, Asymptotic notations that can be big O, omega, and theta. So this method it will solve the recurrence equation, find the final answer from the final solution of recurrence relations. We can find the time complexity. For example, MERGESAT. Time complexity is T of n is equal to R of n log n using the recurrence equations. So T of n equal to 2 T of n by 2 plus n. So this recurrence equation can be solved using induction method. From the answer, we can derive the time complexity order of n log n. So what this equation represents? So T of n, time complexity on input size n, which is equal to 2 times of T of n by 2. So the given problem is divided into two sub-problems. So that is called 2. Each sub-problem have the size of n by 2, n by 2. So total will be n. So n by 2, the size of the given problem n is divided into n by 2 plus n by 2. So mathematical analysis can be used to check the correctness of algorithm and to find the complexity of algorithm. And the third one is proving loop invariance. So when we write for loop, while loop, there is a looping variable. For example, for I equal to 1, I less than n. So I is a looping variable. We have to specify I less than n, the condition where the loop will be terminated. If the condition reaches, the algorithm will be terminated. So to check the correctness of these type of algorithms, we can use mathematical induction method. And proving properties of recursion. We know recursion, there's a base case that should be verified. That is the termination statement for recursive algorithm. So to analyze the recursive process or recursive algorithms, we can use Mathematical induction method. Validating mathematical formulas used in algorithms. So we are using different formulas. For example, matrix multiplication, C of ij equal to C of ij plus C of ik plus kj, and Prim's algorithm, the formula, matrix multiplication. So these type of problem variable can be analyzed using induction method. Verifying formulas for arithmetic geometric sums, recurrence solutions, matrix exponentiation, which are the essential for algorithm times. This can be verified by using induction method. Thank you.